So now let's talk about Newton's second law. So there is a force, right? So there are forces, and forces, what they do is they change the velocity. They cause objects to accelerate, change velocity. Remember, acceleration is equal to delta V over delta T, right? So delta V is a change in velocity. So Newton's second law says that the acceleration produced by a force is proportional to the force, right? And inversely proportional to the mass. What does that mean? Well, the more force you apply, the more acceleration. The more mass an object has, the less acceleration. That's basically what it means. These are vectors, so the acceleration is a vector, the force is a vector, so they have the same direction. So this force that appears here in Newton's second law is actually the net force, right? Is the net force, which is the sum of all the forces acting on a body. So you have all these forces acting on a body. You can have a body, right? So you have a normal force, you have a weight, so you have a tension here, and then you have friction, right? So you have four forces here, right? So then what is the net force? Well, the net force is the addition of, this is the normal here, the addition of all these forces. So that's the net force, and that is a term that appears here in Newton's second law. And the acceleration is going to have the direction of that net force. The most common way in which you see Newton's second law written is this form here. It says F is equal to ma. Let's look at a simple example here. We have a ball that is thrown, and let's say there's a wind. A wind produces a drag, and there is also the weight. Those are the two forces acting on the body, right? So what is the net force? Well, we add these two vectors, so that produces this resultant vector here, and the acceleration is going to have the same direction of this vector here, and it's also going to be proportional to the length, to this length here of this vector. Units of force, so we are going to use two types of units, the international units, so those are the newtons, and the British units, the US units, and those are the pounds, right? So the pound is a unit of force. So a pound is roughly about 4.45 newtons. So your weight, let's say your weight is 150 pounds. Your weight in newton is going to be roughly about 600 newtons. So those are units of force. So 1 Newton, what is 1 Newton? Well, 1 Newton is the force that you need to apply to 1 kilogram, which is roughly 2 pounds, to produce an acceleration of 1 meter per second squared. So that's the definition of 1 Newton. Let's look at a simple example here of applying Newton's second law. We have a plane, and the plane has a mass of 51,000 kilograms, so that's a huge mass, and it's at rest. So then you turn the plane engines on, and then there is a full force, right, applied on the plane. That's a thrust force, right? And then the plane goes through the runway, travels 940 meters, which is roughly 1 kilometer, and it reaches a speed of 70 meters per second before takeoff. So the question is, what is the force applied by the engine on the plane? So, well, we're going to use Newton's second law, so the first thing is useful to do is draw a picture. So we have the plane here at an initial stage and a final stage. We have that initial position is 0, initial velocity is 0, the final position is 940, and the final velocity is 70 meters per second. So we want to find the thrust, and for that we're going to use Newton's second law, which is ma. So we need to find a. We have the mass is given here, so we find the acceleration, and with the acceleration we use Newton's second law to solve the problem. So let's see how to do that. So we know the final velocity, we know the initial velocity, we want to find the acceleration, and we need to find delta x. Delta x is x final minus x initial, right? So that's 940 meters. So now we can solve for the acceleration in this equation. We get this equation here, and then we put the final numbers. So we have 70 meters per second squared divided by 2 times 940, and you get that that is 2.61 meters per second squared. That's a small acceleration. Remember, g, the acceleration of gravity, is 9.8 is 9.8 meters per second squared. So this is about 1/4 of the acceleration of gravity. So this acceleration is about roughly about 1/4 of g. So now that we have the acceleration, we can solve for the force by using Newton's second law, and we get that this is 133,000 newtons. To have an idea of the size of this force, remember that your weight is roughly 600 newtons. So that's a huge force. So remember, the acceleration is about 1/4 g. It seems reasonable for an airplane. And so, the engine produces a thrust that makes sense. So whenever this is a very important step in solving problems, or you always have to think of your results and make sure that they make sense and they are reasonable. So okay, so now we're going to talk about free body diagrams, and free body diagrams is a very important tool to solve problems. What it is basically a drawing with all the forces. So let's just go and do an example here. We have a car that is parked on a hill and it's not moving, right? So let's draw a free body diagram. So the first thing we do is we draw a coordinate system. It could be an inclined coordinate system. So you'll see that for these problems where you have inclined planes, these are the most convenient ones, right? So that's your coordinate system. That's the first thing to do. And now we draw all the forces. What are the forces that we have here? So we're going to have a normal force, and we label that force. It's important to label them, right? We are going to have the weight, right? And we also label that force, and this angle here is going to be theta, the same angle. And we should have a friction force that opposes the motion here, right? So this is this force here. So that's the friction force. So another way to redraw this free body diagram is to just draw the forces, W, normal force, and weight, and then this angle here. One important thing that you need to think when you're drawing free body diagrams is that this is a normal force. It looks like a W. A free body diagram should be allows you to write Newton's equations. So that's important thing. So remember, draw a coordinate system, draw all the forces with labels, and draw all the angles that appears in your free body diagram. As you can see, this would be the appropriate coordinate system, free body diagram. So let's do another one here. So we start by drawing our coordinate system, right? So then we draw all of our forces. So we remember to put names on things, label things, right? So what are the forces acting here? So we have weight, we have tension, we have normal force, and we are going to have friction. So those are the forces that appear there, and as you can see, So this is the right one. And so, and these two have to be equal because it says the car is moving at a constant speed. Constant speed means acceleration is equal to 0. That means the force is equal to 0. This is the net force. Therefore, this tension here has to cancel the friction force here. There is another important law in dynamics that we use is Newton's third law, and that is action-reaction. So basically, if this hammer applies a force to the nail is going to apply a force to the hammer, and those forces are equal and opposite. And a key important point is that these are forces applied in different objects. The hammer is applying a force on the nail, and the nail applies a force back on the hammer. Okay, so here is a drawing that depicts that better. So we have a box B that applies a force on A. So this guy here is a force applied on A. It's force of B from B on A. So then A, by Newton's third law, is going to apply a reaction, a force of A on B. And these two forces are equal and opposite. It's called an action-reaction pair. And they are also applied on different objects. So you cannot add these two forces. You cannot add them because they are not acting on the same body. So Newton's third law, every force occurs in pairs, action-reaction. They act on different objects and they have equal and opposite magnitude. So Newton's third law is a very important law. It's basically the law that allows you to move. For instance, the friction, right? So you the surface, you applied a force on the surface, and the surface applies a force back on you. That is the force that allows you to run or to walk. It's the force that allows a car to move, or is the force that allows a rocket to go up, right? So the rocket expels its gases, and the gases applied a force back on the rocket.